So if you're like me, you've probably been using relational databases for as long as you can remember. You know, back in the 90s, I used Oracle, SQL Server, and then in more recent years, I used open source databases like MySQL and Postgres. Effectively, relational databases were simply the place to store your data. And there were several good reasons why that was the case. One, SQL is a nice high-level declarative query language. You simply say what data you need, and the database server goes and figures it out. You don't have to worry about the low-level details of how the storage is organized. It optimizes the queries and so on. Plus, you also have ACID transactions. You know that if you perform a series of updates, those updates will be performed in their entirety or not at all. That's a very simple, easy-to-use programming model. And then in addition, you have the ability to define constraints that protect the integrity of your data against programming errors. So I think all of those reasons make relational databases very, very attractive. But in more recent years, we've seen the rise of these so-called NoSQL databases, these non-relational databases that in some situations provide significantly better performance and scalability. And later on, I'm going to talk about those in a lot more detail. And we've also seen in sort of the past year the emergence of these so-called NewSQL databases, which are relational databases that have a different architecture to the traditional relational database that can also give you much better performance and scalability. So sort of this database world is kind of undergoing somewhat of a shift. And so in this talk, I'm going to just describe my experiences experimenting with various NoSQL and NewSQL databases. I've spent much of the past year or so porting use cases from my book, POJOs in Action, to various NoSQL databases. And then in the past few months, I've been experimenting with VoltDB, which is a NewSQL database. And so I'm just going to share with you what worked, what was pleasant, and what was not. So for those of you who don't know me, I'm Chris Richardson. I actually grew up in England and then moved to California 20 years ago, which might account for my transatlantic accent. Now, I was in China a couple of weeks ago, and folks there thought I was American, and just. I actually got my start programming in Lisp quite a long time ago in the late 80s, back when AI was very, still quite popular, and Lisp being one of the early dynamic object-oriented languages. Eventually ended up in Java, wrote the book POJOs in Action, which is all about how to build apps with lightweight technologies, or so-called lightweight technologies like Spring and Hibernate. That came out about 6-7 years ago. And then back in 2007, I started tinkering around with this obscure little thing called Amazon EC2. And that sort of turned into an open source project and eventually turned into my startup Cloud Foundry, which was then acquired by SpringSource back in 2009, shortly before it was acquired by VMware, which is where I am today. And these days, I'm a developer advocate for Cloud Foundry, so I just fly around and give talks and occasionally write code. Recently, it's just been a lot of flying. So, there's really sort of two parts to my talk. The first is really kind of what is this NoSQL thing all about? What is NewSQL all about? Why would we want to use it? So I'm going to begin by talking about that. And then later on, I'm going to dive into the case study and just show you how I re-implemented a use case from my book using Mongo, Cassandra, and VoltDB. So in the book, the sample app was food to go. So it was an online takeout, takeaway delivery service. So the idea is that a user would go to the website, type in their delivery address, the delivery time, and then the system would show a list of restaurants that could deliver to their home or office. And then they'd pick a restaurant, browse the menu, pick what they wanted to order, and then click the buy button, the food would get delivered. So this was back in 2006, and so sort of naturally it used a relational database. And had that been a real application, a real startup, and if it had been successful, then probably by now it would have encountered a number of growth-related challenges. It would have to deal with increasing traffic, just transaction volumes. It would have to deal with increasing amounts of data. They'd probably want to distribute the application across multiple data centers, both in order for a disaster recovery strategy. You know, you can't stop people ordering food just because of a hurricane, for example. But also in order to be close to the user, minimize network latency, and so on. And then they'd probably have to deal with increasing domain model complexity. As time goes by, your domain model gets more and more complicated. More relationships, more classes, and so on. So interestingly, in trying to solve those problems, it's quite likely that the architects, developers, etc., would sort of run into the limitations of relational databases, namely lack of scalability. Relational databases really don't scale well. You can't just keep adding boxes to a standard relational database. It's difficult to build a distributed database infrastructure where multiple databases are running in multiple data centers and everything's syncing up nicely. Schema updates are a problem. In many databases, you know, you can easily modify a table by just doing older table add column, but what if that table has a large number of rows? In some databases, adding a column to a large table could take many hours. You know, you might have could come close to the sort of the maintenance window eventually. So there's a big problem there. And then plus there's just the classic object relational impedance mismatch. On the one hand, you've got your nice rich domain model, you know, lots of relationships, inheritance, and so on. And then on the other hand, you've got your flat relational schema. And like, how do you map between the two? Oh, our mappers do somewhat of an okay job, but in the general case, it can be quite a challenge. So there's a whole bunch of problems. And then also, you have to deal with semi-structured data, entities with a varying number of attributes. And since tables have a fixed number of columns, semi-structured data really doesn't fit well with the relational model. So, you know, what can you do about it? Well, one option is you spend a bunch of money. Well, yeah, and there's sort of two ways of spending money. One is to buy a lot of high-end servers, and high-end database servers, and enable Larry Ellison to sort of buy more yachts like the one on the top, right? That was his old yacht. And you know, and there's a lot of, I mean, probably many of you in this room work for companies that have solved the problem by just spending millions of dollars on Oracle. And then the other option, which many startups have pursued, is to just go down the route of hiring lots and lots of smart people to build a distributed, sharded database infrastructure. You know, developers were not paid as much as Larry, so we just buy nice racing bikes like that. So that's one option. Another option is to go use a NoSQL database. And as you're going to see, in some situations, a NoSQL database can give you much better performance and scalability. Some of them have a much richer data model that's a closer fit to your domain model. Plus, they tend to be schemaless as well. So the schema update problem of having to go through and touch every single row in your database goes away. But on the other hand, there's sort of no such thing as a free lunch, and so NoSQL databases tend to have a limited transaction model, no more ACID. You can typically only update a single storage unit within a transaction. So that takes some getting used to. There's also sort of more relaxed notions of consistency. If you perform an update and then follow it by a read, maybe you'll see the updated data. Maybe you won't, at least not for a little while. You know, once again, that's kind of alien. And then they tend not to have the ability to define constraints. So you've sort of got to push that up to the application level. So one of the databases I'm going to talk about, NoSQL databases, is MongoDB, which is sort of hugely popular. So it's a document-oriented database. When I first heard the term document, it was like, well, what's that? XML? Word? I don't know. But it turns out that a Mongo document is a JSON object. So it's a collection of name-value pairs where each value can itself be another object, or it can be an array of values. And so you've got this nice recursive data structure, and these documents can actually be arbitrarily large, up to kind of this measured in the megabytes. And then you have and then they're stored on disk as a nice, efficiently stored on disk as just a sequence of bytes. So you're reading and writing these documents just using serial I/O. Whereas, you know, if you imagine having some complex structure and mapping that to a relational database, that's lots of rows and lots of tables, and hence lots of random I/O, which hard drives are not really good at. So MongoDB can store things quite efficiently. Now a set of documents forms a collection, so that plays the role of a table in Mongo. And then a set of collections forms a database, which is like a schema, and then a server has a set of databases. So that's kind of the model. Writes in Mongo are really fast, so they're actually asynchronous. So you can keep sending when you write to the database saying insert this document or set of documents, the database actually doesn't respond. It's just one-way packet as a packet just going into the database. So you can keep blasting data into the database and never having to wait for a reply. So that's really, really fast. But if you need to kind of wait until you know that those updates succeeded, you can call getLastError, which makes a synchronous round trip, and then waits until those writes have been replicated to the required number of servers and maybe written to disk. So you have control over that. And there's a lot of scenarios where you can really leverage the ability for Mongo to just, you know, blast data into Mongo. It's also very scalable. It will basically transparently partition your data across a series of shards. And each shard can be what's called a replica set, which is effectively a generalization of sort of master-slave. So each shard has a master, and then one or more secondaries, and then if the master crashes, the remaining servers sort of talk amongst themselves and elect a new master. And that's just fully automatic, so it's this sort of nice, scalable, self-healing database infrastructure. There's various use cases for it. One is because of the nature of the writes, it's very good for these high-volume write scenarios where you just, like logging or analytics, where you're just blasting data into the database. And then because of its data model, it's good for storing complex data because it can store it very efficiently. Also, it's good for storing semi-structured data as well, because the documents within a collection don't have to have an identical structure. They should sort of have a similar structure just sort of to preserve your own sanity, but they don't have to have an identical structure. And it's in use by quite a few startups, Shutterfly, Foursquare, and so on. So that's Mongo in sort of a nutshell. So the other NoSQL database I want to talk about is Cassandra. Now it has a very different data model. It's a column-oriented database, which is probably one of the most confusing terms out there because columns here are nothing like columns in the relational world. They're much more just like an entry in a map. So a column has a name, column has a value, and it also has a timestamp that's really just an integer saying when it was last updated. But the critical thing to remember is that the column name and the column value are just values. They can be numbers or strings or booleans, timestamps, and they can also be composite values, which are collections of primitive values. And so it's very much just like an entry in a hash map. And then a set of columns forms a row that has a row key. And then a set of rows forms a column family, which basically plays the role of a table. And then a set of column families forms a key space that's like a database schema. So it's a different model. And the fact that it uses column as a term just really leads to confusion rather than helping. So then, you know, how do you manipulate these column families? So the basic operation is insert that takes a key, takes a row key, and then one or more columns, and just inserts those columns into the specified row. So here we're the key is K1, and then the new column values are N4, T4, and TS4. And that column just gets inserted into row K1. So that's pretty straightforward. And it really is just like inserting an entry into a sort of multi-dimensional hash map, actually. And then the way you get data out is by using a slice operation that you specify the column family, you specify the row key, and then you specify a start column and an end column. And what you get back are those columns whose names fall within that range. So in this case, the start column is N2, the end column is N4, and so you get back columns N2, N3, and N4 because their column names fall within that specified range, but not N1. So you're just getting a slice of columns out of the specified row. Another interesting feature of Cassandra is that it has tunable reads and writes. So basically what this means is when you do a read or when you do a write, you can actually specify how many servers well, in the case of a write, you can specify how many servers that data should get written to before Cassandra replies back to you. So in the Cassandra model, your data is replicated some number of times. So one option is you just say write to just one of those replicas and then return back to me. Or you can say write to a quorum or majority of replicas and then return back to me. Or you can actually just say write to any node. Even if it's not the node where that data belongs, just write to it. And then eventually the data will get replicated get sent to all of the replicas. And then there's the notions of if you've got a multi-data center version of Cassandra configuration, you can say write to a majority of replicas locally, or write to all of the replicas everywhere. So if you really need data to be persisted and need to know that it's been persisted everywhere within your globally distributed clusters, you've got that option. And so this sort of spans the whole spectrum. So on the one at the top, you're only talking to one server, which sort of minimizes response time. And actually, because you're just talking to any server, you have higher availability. Whereas down the bottom, if you're talking to all replicas, that's going to take longer because you're talking to many servers. So you've got higher response time. And there's also an availability issue as well. So you get to trade off, availability and response time and data consistency. So it's really interesting. And then, as I hinted at, Cassandra is very scalable. Within a data center, you can just keep adding servers to a cluster, and it just scales. Plus, you can actually span these clusters across multiple data centers. If you go look at what Netflix are doing, they're building Cassandra clusters that are spread across multiple Amazon regions, sort of effectively building this global database infrastructure, and that's just sort of working pretty much out of the box, which is really, really neat. So, various use cases for Cassandra. One is just because of its scalability, it's really good for storing just humongous amounts of data. It's also good if you want to build a multiple data center distributed database. And then because of the way writes work, it's really good for logging, because you can keep just blasting data into it. And it's also good for scenarios where, because you can write to any server, not the ones that are actually meant to be storing the data, it's good for scenarios where you want to have high availability writes. And it's used by various companies, Netflix, Facebook, Dig, and so on. And there's quite a few other NoSQL databases. If you go to NoSQLdatabase.com, they're listing, there's like 120 plus different databases out there. It's just awful lot. So if you have a favorite, you work for a NoSQL company, I apologize for not mentioning your product. Okay, so spending a lot of money is one option. Using a NoSQL database is an option. Third option is to use a so-called NewSQL database. And so these are relational databases that have SQL and ACID transactions, all that sort of good stuff that we're familiar with, but they have, as you're going to see, a radically different architecture that gives them much better performance and scalability in some situations. And there's various NewSQL databases out there. It's kind of somewhat of a loosely defined category in the same way NoSQL is somewhat loosely defined. So I've been playing with this one called VoltDB. And one of the main people behind VoltDB is Michael Stonebreaker, the sort of relational database pioneer. And he has a number of interesting things to say about databases. So one of them is that his argument is that a traditional database has really been architected for 1970s hardware. And, you know, if you think back to the 70s, if you were born then, you know, computers were quite different. They were really slow. They didn't have multiple cores, and they really didn't have much memory. You know, like when I was in university, I think the university mainframe had 16 meg of memory, right? Which, you know, it's kind of silly. So his argument is, well, databases were in fact pretty much designed for that world. And then you fast forward, right? And, you know, machines are many orders of magnitude faster. They have many orders of magnitude more memory, and they also have many cores, right? You can quite cheaply go out, you know, like my MacBook, it's got 16 gig of memory and 4 cores, and really didn't cost very much, right? And his argument is that traditional databases aren't designed for the modern world. And they did an experiment, which was written up in this Through the Looking Glass paper, where they actually looked to see where a database with a traditional architecture spent its CPU cycles, and basically 87% of those CPU cycles were wasted in, quote, overhead operations like logging and latching and buffer management and so on. And there's sort of this kind of interesting point where he says that, you know, throwing a lot of memory at a traditional relational database, which is our standard approach, is not quite, doesn't give you the same result as an in-memory database, because they're just architected very, very differently. And so his company has created VoltDB, that's this open source in-memory relational database. So first and foremost, your data lives in memory, but, you know, because of risk of power failures and so on, it does give you some durability options. So data gets replicated between servers. There's also the option of snapshotting the server state to disk periodically. And then in between snapshots, it will actually log the execution of stored procedures that modify the data. And so if the database ever needs to recover, it takes the latest snapshot and then replays the log to recover. So you do have durability, but it's not first and foremost designed as a disk database. It's first and foremost designed as an in-memory database, which makes it very, very fast. And then it's very scalable. People have had some really interesting results, like scaling it up to 39 servers, for example, and handling a massive transaction volume. So I'm going to talk more about those in a little bit more detail, but I think it's kind of interesting point I'd like to make is that even, you know, regardless of whether you're using SQL, NewSQL, NoSQL, I think we're going to move to this sort of polyglot persistence world where different modules of our application are going to use the database that's best suited to that module. So if you're storing social data, you'll do that with a graph database. Whereas if you need ACID transactions, you'll use a relational database. Whereas if you're storing complex object graphs, you'll use a document database, and so on. So no sort of one database to rule them all. And then, you know, to help out in that world, there's the Spring Data project, which aims to simplify the development of applications that use NoSQL databases. And that has support for NoSQL databases like Mongo and Redis, Neo4j, and so on. Okay, so that's sort of the motivation for all of this. So kind of want to sort of dive into the case study and just look at the basics of persisting entities in these different databases. You know, storing them by saving entities and then retrieving them by primary key. So the main use case in the food-to-go application is the place order use case. I kind of went through that earlier. The customer enters the delivery address and the time. The system displays the restaurants that can serve that delivery address at that time. Customer picks a restaurant. The system displays a menu. Customer selects the menu items, and then the customer places the order. So you could imagine that supporting that use case is a domain model that looks something like this, right? I mean, this is really, really primitive, but it makes the point across, makes the point. So you've got a restaurant entity that has a primary key, it has a name. It has a service area that's a collection of zip codes that the restaurant will deliver to. So we're not doing geo search, right? Just doing zip code-based definition of service area. Then the restaurant has opening hours. That's a collection of time range objects. And each time range describes one time period on a particular day when that restaurant is open. And then there are menu items as well. So a menu item has a name and a price. So a real simple domain model. Then you can imagine that you could map that domain model to a database schema. So we've got the restaurant table, we've got the zip code table, and time range table. And the latter two tables have a foreign key back to the restaurant table. Pretty simple mapping. Now, if you were implementing this with a relational database, you'd have your choice of JDBC-based frameworks. So you could use Spring JDBC or MyBatis or Hibernate or JPA. There's just tons and tons of different frameworks out there for you to use. And then, we've got methods like add, which persists a restaurant, find details by ID that retrieves the restaurant. It's pretty straight. You could just easily imagine how that would be done with a relational database. But, with a NoSQL database, what do? How do you map this restaurant aggregate to the storage model of the database? And then how do you implement the repository? What's the API? So, let's look at this, how you'd solve this with MongoDB. So Mongo, and we've seen this already, it's very straightforward to map aggregates or your domain objects into a Mongo document. So, here's a document that sort of contains some of the information about the restaurant. So restaurants have a name. Well, the document has a name attribute. The restaurant has a service area, so does the document. Then opening hours is a list of time range sub-documents. So it's a very, very straightforward mapping from your domain model into a Mongo document. So that's the mapping side of things. And then what about the repository? Well, one of the nice things about Mongo is that Spring Data has support for that. In particular, it provides a Mongo template that, in the same way as the Spring JDBC template kind of hides all the details of using JDBC, so the Mongo template hides a lot of the details, argue some messy details, though less messy than JDBC, of using Mongo. So for instance, the add method just calls Mongo template insert, passing in the restaurant and the name of the collection that you want that entity persisted in. And under the covers, it's taking that entity, turning it into a Mongo document, and then saving that Mongo document in the specified collection. And that actual mapping from object to document is, by default, it works using bean introspection. So it just looks at the properties, and each property just maps to an attribute of the corresponding document. And for collection properties, then that generates sort of a collection valued attribute. So it's just a very straightforward mapping that you can then override by using annotations. So if you go look at the docs, there's a whole set of annotations that you can use to control the mapping. And then find details by ID actually executes a query. So there's this query helper class where you can just say query where the underscore ID, the document's primary key, is the ID that's passed in as an argument. The restaurant.class is the target class, and then you're querying the available restaurants collection. So under the covers, it's actually executing a query, then iterating through the documents, turning each document, mapping each document back into a restaurant object, and just returns the first one. So all of that's encapsulated within the Mongo template, which is quite nice. And here's the Spring Java config that's setting that up. So this is defining two beans. The first is a Mongo that's the Mongo equivalent of a data source. And then the second is the Mongo template that just gets injected with the Mongo. So we're creating a Mongo template that's talking to the specified database. So pretty straightforward API. So that's Mongo. What about Cassandra? So there's a couple of different options with how you persist or how you map entities into a into a Cassandra column family. So one option is just to have a column per attribute. So that obviously works nicely for scalar, simple valued attributes like the name and the type. So, entity 1 has a name column whose name is Ajanta, whose name is name and whose value is Ajanta, and then another column whose name is type and whose value is Indian. So that's pretty straightforward. But then what about properties that are collections? And so the scheme I use there is that the column name that it gets mapped to, so each element of that collection gets mapped to its own column, and the column name is like the path or the expression that you would use to access that value. So service area is a set, or you could think of it as an array, and so you have service area paren 0, service area paren 1 to access those, to store those two elements. So it's a little weird, but it's a way of generating unique column names for an arbitrary sort of tree structure object. And then for opening hours, you actually use the dot notation to access the sub-elements. So that sort of works quite well. So basically what we're doing, we've got this entity, or this aggregate, and we're basically flattening it out into a set of effectively name-value pairs that then get mapped onto columns. So that's one way of doing it. And then the other way of doing it is just to use a single column, which is the serialized representation of that entity. And for that, you could use JSON, you could use XML, you could use Java serialization. It doesn't sort of pick your favorite there. And that's actually the one I've been working with. It's very easy to use something like Jackson to serialize, deserialize into JSON, and then rather than having to do the former mechanism. The sort of downside of this is that the entity gets stored as this opaque string, and so there are features of Cassandra that you can't use, such as secondary indexes and so on. But for this particular use case, this representation is fine. So Spring Data doesn't support Cassandra, but I ended up creating my own Cassandra template that just sort of wraps the rather complex Cassandra API. And the actual Java library that I used here was called Hector, which is one of the Java APIs that's available. Netflix also have one as well, though I haven't actually looked at that yet. And I didn't want to go, there's a lot of messy coding details, so the key point here is, well, I just built something on top of Hector just to simplify its usage. Okay, so that's the NoSQL databases. Well, what about NewSQL? Well, the interesting thing about VoltDB is that it's relational, so you can use the original schema, and you can use standard SQL, so it's sort of familiar, right? But on the other hand, you actually have to write stored procedures in Java and invoke them through a proprietary interface. They actually do have a JDBC driver for invoking stored procedures, but it seems it's not quite there yet. And then you also have to come up with a partitioning scheme for your data. I'm going to talk about what that means in a minute. So first off, stored procedures, well, they're a pretty integral part of how VoltDB works. So for instance, the way replication works, where you've replicated your data across multiple servers, it actually executes your stored procedure against each replica of the data. So it's not shipping, it's not applying it to one replica and then shipping the changes. It's actually re-executing your stored procedure against each replica of the data. And then the way the logging works is that it actually records the invocation of your stored procedure. And then if it's doing a recovery, it just re-executes your stored procedures against each replica. And then also, each stored procedure invocation is a transaction. So you don't have any explicit transaction begin, commit, rollback commands in your code. You just call a stored procedure, and that is just automatically executed as a transaction. So it's quite different than what we're sort of used to. And then the other part of this is you've got to define a partitioning scheme. And what that basically means is for each table, you have to specify which column should be the partition column. And then the value of that column for a given row determines which partition that row lives in. So in my example, I use the primary key of the restaurant as the partition column. And so a janitor would live in partition 1 and egg shop would live in partition 2. Basically, it's just taking the mod value or hash value of the column value. And then for the I actually use the restaurant foreign key as the partition column in the other tables. So then when you set up a cluster, you end up with something that sort of looks like this. So if you have 3 servers and you say, I want 2 partitions per server, and then I want 2 replicas of each partition, then you end up with 3 different partitions that are distributed like this. So partition 1 has 2 replicas A and B on servers A and B, and then partition 2 has 2 replicas on server B and server C, and then partition 3 is on server C and server A. So that's kind of sort of how it would end up looking when it's up and running. And then there's a really interesting interaction between stored procedures and partitions. So in order to make your code, if you want your code to run as fast as possible, you should write what are called single partition stored procedures. And these are stored procedures that take a partition key as an argument. So for instance, the ID of the restaurant as an argument. And then they should just execute, every SQL statement that they execute should have a where clause that involves the partition column. Basically, partition column equals partition value. And so if you write stored procedures that match that pattern, then VoltDB will execute them very efficiently by basically examining the argument that you pass in and saying, oh, this stored procedure needs to just be executed against this partition. And so it just sends it to the right place and executes it like really, really efficiently. Whereas if you write what are called multi-partition stored procedures, which are ones that execute SQL that don't involve the partition key, then those stored procedures basically, well, the SQL statements need to be executed against all of the partitions, and then the results like merge together. And there's like a 10x difference in terms of performance. So single partition code goes really, really fast. Multi-partition code, not so fast. And then, as I mentioned, I used this partitioning scheme initially. So the partition key is the restaurant ID, and then the foreign key in each of the tables. And I got pretty good performance, by an order of magnitude faster than MySQL. So I was quite happy with that. And then here's an example of a stored procedure. It's Java, it extends Volt procedure. You can see that it's sort of statically defining the SQL as these public final SQL statement objects. That's really important because VoltDB basically analyzes, you sort of run a compiler over your stored procedures and it analyzes your code. And then you can see here it's like queuing up these queuing up the SQL and then executing it down here. So it's sort of familiar but different all at the same time. And then here's my repository code, where it's just basically taking domain objects, mapping them into arrays of values that can then be passed to the stored procedure. You can't pass Java entities all the way into stored procedures. There's this sort of RPC layer in between. So you have to go through this tedious process of like flattening everything out into an array of objects, or an array of like longs or strings, basically primitive values, which is kind of frustrating. And then the actual API that VoltDB supports is basically call this stored procedure with these values. That's pretty much it. And then it gives you back a response object, which out of that you can get the equivalent of a JDBC result set. Let's skip over the configuration because I don't have time to go into that. So that's sort of the basics of using each of those databases. And for the most part, they all resulted in pretty good performance. Mongo is actually really fast. VoltDB was sort of amazingly fast, sort of using loose terminology, but it was just fast. And then, Cassandra was reasonably fast. My benchmarking was probably somewhat imprecise, but there was very clear order of magnitude differences between some of those databases and MySQL. Even though, for example, the amount of data was small enough to fit into MySQL's memory. Okay, so that was basically sort of primary key-based lookup. So what about queries? This is sort of where it gets interesting. So one of the key queries here is finding the restaurants that are available. And the definition, for the sake of this discussion, is that a restaurant is available if the zip code, if it serves the zip code of the delivery address. So in other words, the delivery address's zip code is in that service area collection, and the restaurant is open at the delivery time. So there's a matching time range object that corresponds to the delivery time. And so you can imagine that the repository has a find available restaurants method that takes the delivery address and delivery time and gives you back a list of available restaurants. So if you were using a relational database, you just do a three-way join between the various tables. And so this is finding restaurants that are open at 6:15 on a Monday that serve the 94619 zip code. So it's a pretty straightforward query. So what about with Mongo? What do we do? Well, interestingly with Mongo, even though Mongo doesn't support SQL or anything like that, it's actually a pretty straightforward query. And the way the Mongo Query API works is you create a document. It's sort of like query by example. So you create a document whose structure kind of matches the structure of the documents that you want to find. So in this case, we want to find the documents whose service area attribute contains 94619. So we just actually create a query document when you just say service area 94619, that will match against scalar values as well as array values. So that's pretty straightforward. And then we want to find documents whose opening hours attribute contains an element that sort of corresponds to Monday at 6:15 or 18:15 in the 24-hour clock. So you have that $LM match sort of special query marker. When you say day of the week is Monday, and then the opening time has to be less than, the restaurant has to be open before 6:15 in the evening, and it has to close after 6:15 in the evening. So it has to be, in other words, it's one way of expressing the fact that it has to be open at 6:15. So, so it's got its own quite rich query language, and then you just execute that query, and you get back a bunch of documents, and you can you iterate through the cursor and process each one. And Spring Data for Mongo makes that quite straightforward. So we construct the query using this query helper class, and then we use Mongo template.find to where we specify the collection name, the query we want to execute, and then the class that we want to map each document back to. And so under the covers, it's constructing the query document, executing the query, iterating through the cursor, mapping each document that it gets back into an available restaurant, and returns the list. So that was quite painless. But how the heck do we do this with Cassandra? Because Cassandra, as you saw earlier, only has a slice operation, right? So interesting thing about slice is that it takes a row key and it takes the start column value and end column value, is that it's actually equivalent. We could actually express the slice as a really simple SQL query. So you can see that on the top right of the screen. So it's sort of, rotating things through 90 degrees in a way. So the slice actually corresponds to a really simple SQL query. So sort of the trick of what we have to do is transform the original three-way join into a query that kind of looks like that. And then once we've done that, we can use a slice operation. So it ends up, basically what we end up having to do is kind of come up with a denormalized representation of the data that can be queried in a really, really simple way. And that's sort of one of the key lessons that you learn from working with, not so much with Mongo, but with Cassandra or Redis, is that because they don't have rich querying capabilities, if you want to query them, you end up having to play these tricks with sort of, as you'll see with denormalization. So, so in the SQL world, if we want to simplify a query, sort of the standard technique is, at least in terms of eliminating joins, is to denormalize your data. So in other words, pre-join that data. And then once you do that, that three-way query, kind of three-way join, collapses into a much simpler query. So there are no joins. There's just two equality operations and then a couple of range comparisons, right? Close time is greater than some value. Open time is less than some value. Another thing we can do that's sort of a little interesting is just simplify the where clause by not worrying about the opening time. So the query, the database is going to give us back more data than we need, but then we can filter that out in the application. There's nothing wrong with doing that, right? We're just sort of, from the relational world, it's sort of perhaps less efficient, transferring more data over the wire, but it's very workable. So you can see that we're sort of gradually inching our way towards a query that's a lot simpler and kind of basically matches what a slice is capable of. And then the other sort of thing that we can do is, instead of having two equality operations, if we actually just pre-concatenate those values, we only have one equality in our query. Probably the guy who invented sort of the concept of normalization is like spinning in his grave if he's actually dead. But so it's, and DBAs are feeling kind of queasy at this point. But if we sort of go through all of this, we end up with a really, really simple query that just so happens to match what a slice operation is capable of doing, right? Because we've got one equality, so that's basically looking up by row key, and then we have one comparison on one attribute that corresponds to the range part of the slice. So then, we've sort of we've simplified the data and simplified the query, and then we can map that table onto a column family. So the zip code day of the week becomes the row key, the close time actually becomes part of the column name. And then we also just pack the column name with the opening time and the restaurant ID. And the reason I'm doing that is really to avoid having to parse the JSON unless we really need to go look inside it. But those other two values could just go inside the column value. But just by sort of going through this process, we now have a representation of that data that we can then query with the slice operation. And so, for instance, when we execute the slice, we'd get back that specified column. And then we can look at the opening time and say, well, the opening time is before the delivery time. Therefore, this restaurant matches our query. So, it's a little bit involved, but it sort of demonstrates that, something that appears on the surface not to support queries can actually be sort of made to support queries. And you actually have to write some code in order to make this work, right? And you're probably going, well, why on earth would I want to do this? But the interesting question is, well, what would you prefer to implement? Some sort of slightly more complex query logic like that, or do you want to build a multi-data center, multi-master database infrastructure from scratch, right? Which one is easy? And I guess I'd argue that you take Cassandra. Out of the box, it supports multiple data centers, but you got to do a little bit of work to support some queries. I'd say that's a win, right? So I think, so if multi-data center databases is part of your future, then it's probably worthwhile. Okay, so a few more minutes remaining. Kind of want to talk about VoltDB. So, it's funny, when I started using VoltDB, I thought, cool, I'll just take my three-way join query and run it. And when I did that, the good news is that it worked, but it was really, really slow. And initially, that was because I hadn't defined any indexes to make it go fast, right? So it was doing a whole bunch of table scans. And so just in the same way that MySQL or Oracle would be slow if you didn't have the right indexes, so was VoltDB. So then I defined them, and then it failed. The sort of the pre-compilation phase blew up because it thought that it didn't support this query. And so that was like a total bummer. Though it's sort of, I've actually been talking to them, and they're working on making it go better, go faster, or work better. So perhaps in the very near future, this problem will be fixed. So the next thing I tried was I had to denormalize the data to get rid of the join, which seems a little weird. So I ended up with a situation, once I did that, the inserts were still really, really fast, like orders of magnitude faster than MySQL, but the queries were only slightly faster than MySQL. So that wasn't so great. So then the other thing I did was to pick a different partitioning scheme, so I actually partitioned by zip code instead, which meant that the add restaurant was a multi-partition stored procedure, and the find available restaurants stored procedure was a single partition. Previously, it had been the other way around. And then at this point, once I did that, then queries were really, really fast, like 20 times faster than MySQL, but the inserts were a lot slower. So that was kind of disappointing. But I guess you sort of end up that's sort of, to a certain extent, that's kind of the nature of these partitioning schemes in distributed databases. They optimize certain use cases or certain queries at the expense of other ones. And so, so in essence, what I found is I could do either inserts really, really fast, which is good for which might be good for some applications, and queries were only slightly fast, or I could do slow inserts and really, really fast queries. And you could argue that for many applications which are read-heavy, then that would be fine, right? If, you know, if inserts just take twice as long as on MySQL, is it that bad because they're relatively infrequent if the queries are like 20 times faster? So it's sort of an, you know, kind of pick your, you got to think carefully about which partitioning scheme works best for your app. So, you know, that's my talk. So sort of in summary, you know, we've looked at SQL, NoSQL, and NewSQL. And I think it's fair to say that different databases make different trade-offs, right? And you look at the traditional relational database, it's got SQL and ACID, and we're all very familiar with it. Yet on the other hand, it doesn't, you know, there's performance and scalability issues, and just schema updates can be a problem. And then you look at NoSQL, and that's got great scalability and performance, but doesn't have ACID and has lack of querying. And then you look at NewSQL, that's got ACID and SQL, and it's kind of familiar. But then, you know, it's not all the not all use cases are very performant. And then it's got all of the limitations of the relational model, namely around schema updates and handling semi-structured data. So there's sort of, you know, it's kind of like there's no silver bullet here. You know, you just have to pick the databases, pick the database that really works best for your application. So, you know, rather than just because NoSQL is cool right now, doesn't mean that you should rush off and start using it. You really need to do a proof of concept to see whether it really, really works for your application. And I think, you know, polyglot persistence is definitely worth thinking about. And you probably want to encapsulate your database access code so that you can switch databases if you ever find you made a mistake, right? And then, you know, an interesting thing is like, well, what do you do if you're a startup? Because on the one hand, you know, these databases are all about solving performance and scalability problems, but if you're a startup and you don't actually have any customers yet, you don't have any performance or scalability problems. And so, you know, maybe you should use relational technologies that have a very mature set of tools that enable you to iterate very, very quickly and not jump into the whole NoSQL route or NewSQL route until you've actually figured out that you really do actually have a viable business. So kind of interesting kind of decisions to be made. So anyway, that's my talk. So thanks for your time, and I hope that you found this useful. And we have like 2 minutes, 3 minutes for questions.